fast as it can. Also, if you've ever blown a light bulb before, that's because you got too much current flowing through and it causes the filament to basically burn and it snaps. So resistance is good at times. The symbol, and so from this you create a resistor. The symbol for resistance is cleverly capital R. What?
I said, who would have knew?
How'd they come up with this stuff? So if we were in the hallway and we were trying to get out that exit, well, that'd be a lot more difficult than trying to go out that exit. Why? Why is that way longer than that? Parts go over there. Why is it harder to go out that door than that door?
Longer.
So one of the things resistance depends upon is the length of the wire. Now, think about the doors. We're trying to get out of the room because of the fire in the corner. We're trying to get out the door. What would make it easier to get out the door?
That door wider.
Yeah. So how much room is there, how wide the hall is, or how wide the door is also matters. And so the bigger the area, the cross-sectional area, the wider the door, the less resistance there is. And the one other factor here is known as resistivity. Resistivity is it's a material dependent thing. That conductors, it is a low number. For insulators, it's a high number. Give you just some sense. The resistivity of copper, Cu for copper, is approximately 1.7 times 10 to the negative 8 ohm meters.
Is that the same thing as density? Because it looks like the same symbol.
It is the exact same symbol, but completely different meaning. Because again, we only have 100 characters. We have to reuse them.
We should just make pictures.
You could just make up a character. Yeah.
And they did. Or was this class or the other class? Talk about H bar. That's a particular concept that is H divided by 2 pi, which showed up enough. They said, well, let's come up with a symbol for it. And so they just stuck a hash mark through the H.
What if they went to became a physicist and they said H bar? Like what?
In physics, if you say H bar, people know what you're talking about.
Okay.
Oh yeah, that's in some word processing. H bar is the code word to say, hey, print this. All right, so because it depends upon the length, the longer the wire, the more resistance. The skinnier the wire, the more resistance.
What
Yes.
is that times meters?
Here,
Yeah.
that is a meter, and this is a capital omega. Capital omega, so if the SI unit for resistance is the ohm, named after,
Oh.
and the symbol is a capital omega.
OHN.
Yes. And then potentially, something useful you can pull out of this. If you play Scrabble and other type games like that. There is a unit which is the reciprocal of an ohm. And it is the mho. I've never actually heard it pronounced. I pronounce it mo, but maybe it's mo. I'm not sure, but this is a legitimate Scrabble word. One other unit that they did this with, there is a unit called the Henry, symbolized by an H. Oh, sorry, over here, one other thing. if I wanted to write this as a single symbol instead of refraction, I would write it like that. That's the symbol for the Henry. H 1 over a Henry is, again, never heard it pronounced, but I pronounce it here now. It is a legitimate Scrabble word. To my knowledge, this is the only two that they just changed the order of the letters.
That sounds like a good way to get thrown out of your home Scrabble game.
Yeah. Make sure you have a dictionary which has those words in it.
Make sure not to play Scrabble with you.
I was playing a game of Prolific, which was like a Scrabble knockoff, and I managed to actually get that word. All right. So, if I've got a longer wire, I've got more resistance, and so the symbol for a resistor, just like that is the symbol for the power supply, DC power supply. Symbol for a resistor is basically you take a wire and you scrunch it up, and so the symbol for a resistor, and that's to represent a whole bunch of wire. Therefore, let's connect a couple pieces here. I got my power supply, we'll make it a 12-volt power supply or battery. I have a resistor in it, and it's a 3 ohm resistor. There is something known as Ohm's law, which is the voltage is equal to the current times the resistance. So if I want to know the current flowing through that wire, well, I have 12 volts is equal to my current times my resistance, which is 3 ohms. Well, divided by 3 ohms, I get 12 volts divided by 3 ohms. There's the math piece right there. And my units,
Volts per ohm.
Yeah.
volts per ohm is also, it would work, or
Ampere.
amperes.
Amperes. I know the plural of it.
The unit is anglicized, ampere. The person is not. And by the way, volt, named after, it is not. It is one of the few, one of the few units that is named for somebody, but his last name is not Volt. It is Volta. And another one that we probably won't get to is the Farad, named after Faraday. All right. Questions to hear? All right, so probably with the last concept here. I now want to increase the resistance in this because let's just say I've got this 3 ohms here is some sort of application that needs 4 amps would burn it out. How can I increase the resistance so that my current is not as strong? Think of it as you're trying to get out of the room. What can make it harder to get out of the room?
Desk.
What'd you say?
The desk.
Yeah, or we could add more desks to make it harder. So here, if I want to increase resistance, I just add another resistor. I throw a resistor in here. Let's say that's a 9 ohm resistor.
9.
So what's my total resistance now?
12.
Yeah, because I'm going to have current flowing across both of these, so they're going to be experiencing the same, and for some reason it did not want to change colors. So I have 12 volts is equal to my current times 12 ohms. So my current 1 ampere. By the way, resistors that are set up like that are called in series, because the current flowing across one equals the current flowing across another.
I kind of remember doing something with some of this.
Hopefully it brings back fond memories. I'm now going back to my original circuit. I've got my 12-volt battery. I've got my 3 ohm resistor here. Now it turns out they want to use the same basic circuit, except this time they've got a device in there that needs more current. So I need to drop the current. And because of restrictions or tradition or whatever it is, I can't take that 3 ohm resistor out and put a smaller resistor in there. But I need to somehow lower the resistance. How can I lower the resistance of the circuit without removing that power supply or that resistor?
Could you add another power supply?
Add another what?
Power supply?
Ooh, I could do that, not the path I was thinking of, but yeah, we could potentially add another power supply. Suppose we want to add a resistor. How could we add a resistor and drop the overall resistance?
-3.
If you could come up with a negative resistor, you probably could make a fortune.
Add another wire so it could go like avoiding the spark.
Add another wire.
Like go before that so it could go like
So, where? You want
no, just
there?
Cut it out.
If you added a wire there, if there's no resistance, then that doesn't do anything. Or even if there is resistance, the current would split, come back together again, and then still go across that 3 ohm resistor.
I was talking about way to avoid that part. So like
Avoid this
before
part?
it ends.
Do that. Is that not what you're talking about?
okay,
Okay.
Okay, so before the 3. Okay, yeah.
All right, this is known as a short circuit. You got to be careful about that. Some things get short circuited. Current's not going to flow unless there's a path. So if I had if that were my circuit, no, the current is 0 because unless it's going to spark, but current's not going to jump that. If it bypasses, well, if it's a battery, that battery's going to drain really quickly. That's the car battery against the side of my truck. But sometimes the short circuit is on something like this. It's looking for a path. So if I touch one end, suddenly I might be basically creating the path. Electric fences. I don't know if any of you dealt with an electric fence before. Is that a nod back there? Any of you?
I have actually.
Basically, the circuit for an electric fence is you've got the electric wire and you've got a spike in the ground, and that goes until some other endpoint. There's no circuit there, there's no current that's running, but if somebody touches this and the ground at the same time, you now complete that circuit and current flows through. So if I got rubber sole shoes on and I touch an electric wire, hopefully it's not going to shock me because the rubber soles should protect me. Now, if it's powerful enough, it'll go through the rubber, but hopefully it won't. But if I do that and then stick my finger on the ground, that will shock. Or for pets, if keeping pets in, since they're not wearing rubber soled shoes, if they touch the wire, their feet are touching the ground, they will complete that circuit. So assuming that I don't want to short circuit anything, it turns out if I add another resistor here,
Wouldn't that be less ohms than the one that you started with? You have 3 and 3.
yeah. So what happens now, my total basically my current here is 8 amperes. It doubled it.
I'm confused.
Why does adding a resistor cause more current to flow? Well, think about it this way. Treat the width of the door as sort of like the resistance. So we all try to get out, we try to go through that door, and we're limited how many can get through at a time, so that basically limits the number of people that can pass through that point and for a certain amount of time. Suppose we opened up another door. Well, we now have two directions people can go. We can get out of the room faster. We have two paths there. Charges can move faster. Or more charge can flow through in a certain amount of time. Without this here, the resistance to go from this point around to this point is actually infinitely large. So we did add a resistor, but we actually lowered the resistance for this path to go from an infinitely large resistance to 3 ohms. So we dropped the resistance of that path. And I do want to put in one other clarification here. There would still be 4 amperes flowing across that. There would be 4 amperes flowing across this. There'd be 8 amperes coming out of the battery.
So that addition is doing what again?
This extra path is lowering the resistance of this path from infinity to 3.
So it's not getting rid of it completely.
Right, I mean, there's still a resistor there. Or if I did a wire, it lowers, superconducting wire, it lowers it from infinity to 0, or something near 0. So Christmas tree lights, or lights in general, string of lights, you don't want to do Christmas. If I've got my power supply here, and I've got a resistor, and I got a resistor here, and I got a resistor here, if this breaks, I still have 2 paths here. Current is still going to flow through those 2 paths. This is known as in parallel. These resistors are in parallel. So if your lights are hung in parallel or wired in parallel, if one goes out, the others stay lit. If it is in series, as Christmas lights used to be, if one goes out, all of them go out. I don't know if any of you have experienced the trying to figure out which bulb is bad.
Your resistor looks like the Easter man of the stones.
Oh, Easter Island?
Yeah,
Which one looks like?
the resistance. Like the little squiggles. Do you not
Oh.
see it? Like it's a stone face.
That one right
No,
there, if that's
on
like a
top.
nose or up
That's
top?
the main
Oh,
one.
there we go. Yeah, I see it now. That one more than the other 2.
Mm-hmm.
Connecting back to Christmas lights.
Yeah.
So, and now the current design, I think for most lights, depends on how much you spend, is you'll have a combination so that, you'll have a couple in series here, and those are in parallel with others. So if one of them breaks, you still have most of the lights there, but you just have to lose one small strand, hopefully. Anyway, and on that cheerful note, Thursday, final test, start out with any questions, and then after that, do the test, and then you will move off and make other things in the world. Or go to your next class. Whatever's happening.
That's it.